Imagine a long, flimsy piece of spaghetti. It's just been cooked, it's limp, and has no real shape. Now imagine, in less than a second, that piece of spaghetti spontaneously ties itself into an intricate, perfect knot. It does this every single time, without fail, and it does it faster than you can blink. That's basically what a protein does. When a cell makes a protein, it starts as a long chain of smaller molecules called amino acids. It's like a string of beads, one after another. This chain is floppy and useless. To do its job, whether that's carrying oxygen, digesting food, or fighting off a virus, it has to fold into a very specific three-dimensional shape. This shape is called its native state, and the process is called protein folding. The truly mind-boggling part is the speed. A typical protein might be a few hundred amino acids long. It folds into its final, functional shape in microseconds or milliseconds. That's a millionth or a thousandth of a second. This presents a huge puzzle. How does it happen so fast? How does this simple chain know exactly what shape to become? It's not a random process, it's precise, it's reliable, and it's essential for life itself. If proteins don't fold correctly, or if they fold too slowly, things go very wrong. Diseases like Alzheimer's and Parkinson's are, at their core, problems with protein folding. So, the question isn't just an academic one, it's a question about how life works at its most fundamental level. To answer it, we have to look at a paradox that stumped scientists for decades. Back in the 1960s, a scientist named Cyrus Levinthal thought about this problem. He did some simple math. A protein chain isn't completely flexible. The bonds between amino acids have some preferred angles they can twist into. But even with those limitations, there is still a huge number of possible shapes a protein could adopt. Let's say a small protein has 100 amino acids, and let's be generous and say each amino acid can only bend into, say, 3 different positions relative to its neighbor. That doesn't sound like much, but the number of possible total shapes is 3 multiplied by itself 100 times. That's 3 to the power of 100. The resulting number is astronomical. It's a 1 with about 47 zeros after it. That's more than the number of atoms in the known universe. Now imagine the protein trying to find its correct shape by simple trial and error. It tries one shape, checks if it's the right one. No? Okay, it tries another, and another. Even if it could try a new shape at the fastest possible rate allowed by physics, something like 1,000,000,000,000 times a second, it would still take an impossibly long time to check all the possibilities. It would take longer than the age of the universe. Much, much longer. But we know proteins fold in milliseconds. This is Levinthal's paradox. A protein can't possibly be searching randomly for its final shape. There just isn't enough time. So if it's not a random search, what is it? There must be some kind of map or a set of instructions that guides the protein to its destination without visiting all the dead ends. The secret, it turns out, isn't in some external instruction manual. The instructions are built right into the chain itself. They are written in the language of physics and chemistry. To understand the solution, we have to understand the main characters in this story. The first are the amino acids themselves. There are 20 different types of amino acids that our cells use to build proteins. Think of them as 20 different kinds of beads on the string. They all have a common backbone, which is what allows them to link together into a chain. But each one has a different side group, a little chemical appendage that sticks out. And these side groups have different properties. The most important property for folding is their relationship with water. Our cells are basically bags of water. The entire folding process happens in a watery environment. Some amino acid side groups are hydrophilic, which means they love water. They have electrical charges that are attracted to charges on water molecules. They are happy to be out in the open, surrounded by water. Other amino acid side groups are hydrophobic. They hate water. They are oily and nonpolar. Just like oil and water don't mix. These hydrophobic side groups want to get away from the water. They want to hide. This single fact that some parts of the chain want to be near water and other parts want to hide from it is the single most powerful driving force in protein folding. So, when a new protein chain is made, it's floating in the water of the cell. Immediately, chaos seems to ensue. But it's a directed chaos. The hydrophobic, oily parts of the chain start trying to get away from the water. And the easiest way to do that is to find other oily parts of the chain and stick together. They cluster in the middle, pushing the water out. This forces the protein to collapse in on itself. This initial, incredibly rapid step is called the hydrophobic collapse. It's not a gentle process. It's a powerful, almost violent crumpling of the protein chain into a more compact ball. This single step dramatically solves a huge part of Levinthal's paradox. The protein isn't sampling all possible extended shapes. It instantly gets rid of most of them by collapsing into a small, dense globule. The search space is cut down from an astronomical number to something much more manageable. This collapsed state is often called a molten globule. It's not the final, perfectly folded protein. It's more like a rough draft. The overall shape is about right. The inside is oily and the outside is water-friendly. But the internal details aren't locked in yet. It's still a bit wobbly and fluid, hence the name molten. But even getting to this molten globule state happens in microseconds. It's the first and most important signpost on the folding pathway. The protein isn't wandering lost in the wilderness of possible shapes. It has been driven by the hydrophobic effect straight into a small, promising valley. Now, with the protein in this compact form, other, weaker forces can start to take over and do the fine-tuning. These are the forces that create the beautiful, intricate details we see in a finished protein. One of the most important of these are hydrogen bonds. These are weak attractions that can form between different parts of the protein backbone. Think of them like tiny, weak magnets or little strips of Velcro. A single hydrogen bond is very easy to break. But when you get hundreds of them forming all at once, they become very strong collectively. These hydrogen bonds encourage the protein chain to form regular, repeating patterns. You may have heard of them. The two most common are the alpha helix and the beta sheet. An alpha helix is like a spiral staircase. The protein backbone twists around, and hydrogen bonds form between the rungs, holding the spiral shape steady. A beta sheet is when different parts of the protein chain line up next to each other like lanes on a highway and form hydrogen bonds between the strands. These secondary structures, the helices and sheets, often start to form very early, sometimes even as the hydrophobic collapse is happening. Little segments of the chain spontaneously snap into these stable, local arrangements. Now, instead of a floppy, disorganized molten globule, you have a compact structure made of more rigid, preformed pieces. The job is now to arrange these pieces correctly relative to each other. It's like building with Lego. First, you build a few small, solid chunks out of individual bricks. Then, you click those chunks together to make the final model. It's much faster than trying to place every single brick in its final position from the start. So the protein has collapsed. It has formed some local helices and sheets. Now the final adjustments happen. The protein wiggles and shifts, trying to get every single atom into its most comfortable position. This is where other, even subtler forces come into play, like van der Waals forces. This is a very weak attraction that occurs when any two atoms get very close to each other. It's a kind of general stickiness that helps pack the inside of the protein tightly with no empty spaces. All of these forces, the hydrophobic effect, hydrogen bonds, van der Waals forces, are pushing and pulling the protein towards one specific state. This is its lowest energy state. This is the central concept that replaces the idea of a random search. The protein isn't looking for a shape. It's falling into one. Scientists have developed a powerful analogy to visualize this process. They call it the protein folding energy landscape. Imagine a huge, three-dimensional landscape with hills, valleys, and mountains. The altitude at any point on this landscape represents the energy of the protein in that particular shape. High-energy shapes are unstable, like a boulder perched on a mountaintop. Low-energy shapes are stable, like a boulder that has rolled to the bottom of a deep valley. The unfolded protein chain starts at the very top of this landscape. It has a very high energy, and there are a vast number of possible shapes it can be in, so the top of the landscape is very wide and flat. Levinthal's paradox describes the problem of trying to find the single lowest point on this vast, high plateau by wandering around randomly. But the landscape isn't flat. It's shaped like a giant funnel. The top is wide, but it all slopes downwards towards a single, deep, narrow point at the bottom. That point at the bottom of the funnel is the native state, the final, folded, low-energy shape. The protein doesn't search, it just falls. As soon as the chain is made, it starts to tumble down the sides of this energy funnel. The hydrophobic collapse is like a massive landslide, taking the protein from the high plateau way down the funnel walls in a single, swift movement. As it continues to fall, it might get temporarily stuck in small dips or gullies on the side of the funnel. These are intermediate states, like the molten globule, but the overall slope is always downwards. The formation of secondary structures and the final packing of the core help it slide further and further down. Every wiggle and jiggle of the protein chain is, on average, taking it to a lower energy state. It's a biased downhill journey. It doesn't have to try every single path. The laws of physics encoded in the funnel shaped energy landscape guide it rapidly to the bottom. The shape of this funnel is determined by the sequence of amino acids. Change just one amino acid, and you might create a new bump or a ditch on the side of the funnel, which could slow down folding or even make the protein get stuck in the wrong shape. Evolution has spent billions of years selecting for amino acid sequences that not only produce a functional final shape, but also create a smooth, steep funnel that allows for fast and reliable folding. The speed itself is a product of natural selection. A cell can't wait around for seconds or minutes for a protein to fold. It needs its molecular machines ready for action now. So, the answer to how proteins fold so fast is this: they don't search. They collapse and then funnel down an energy landscape that is pre-programmed by their amino acid sequence. The hydrophobic effect provides the initial big push, and then a cascade of smaller local interactions guide the protein the rest of the way home. Of course, the real world is messy. This idealized downhill slide doesn't always go perfectly. Sometimes a protein makes a wrong turn. It might get stuck in one of those little ditches on the side of the energy funnel in a misfolded state. A misfolded protein is not just useless, it can be dangerous. The hydrophobic, oily parts that should be hidden on the inside might be exposed on the outside. These sticky patches can cause misfolded proteins to clump together, forming large insoluble aggregates. These aggregates are at the heart of many neurodegenerative diseases. In Alzheimer's disease, a protein called amyloid beta misfolds and clumps into plaques that gum up the brain. In Parkinson's disease, it's a protein called alpha-synuclein. In mad cow disease, it's a protein called a prion. Prions are especially scary. A misfolded prion protein can act as a template, grabbing correctly folded prion proteins and forcing them to misfold in the same way. It triggers a chain reaction that destroys brain tissue. The cell knows how dangerous misfolding can be. So it has a quality control system in place. It has a special class of proteins called molecular chaperones. These chaperones are like the pit crew for protein folding. Their job is to help other proteins fold correctly. Some chaperones work by simply isolating a newly made protein chain, giving it a protected space to fold without the risk of bumping into other proteins and sticking to them. They create a little private folding chamber. Other chaperones are more active. They can recognize a protein that has gotten stuck in a misfolded state. They bind to it, use energy to unfold it, and then release it, giving the protein a second chance to fold correctly. They are constantly patrolling the cell, fixing folding mistakes, and keeping the cellular environment clean and functional. This whole system, the fast funnel-driven folding process, combined with the chaperone-based quality control, is incredibly robust. The vast majority of the billions of proteins being made in your body every second are folding correctly. It's a testament to the elegance of a solution honed over eons of evolution. For a long time, this picture of the folding funnel was a beautiful theory, but it was hard to prove directly. We could study the starting point, the unfolded chain, and the endpoint, the perfectly folded protein. But watching the journey itself, which happens in a flash, was incredibly difficult. Scientists developed clever techniques to get glimpses of the process. They could use lasers to heat up a protein very quickly, causing it to unfold, and then watch it refold as it cooled. They could use powerful techniques like nuclear magnetic resonance, NMR spectroscopy, which can track the positions of individual atoms in a protein as it wiggles and changes shape in real time. But the biggest revolution in understanding protein folding in recent years has come from computers. For decades, scientists have tried to simulate the folding process from scratch. The idea is simple in principle. You create a computer model of a protein chain, with every atom represented. You tell the computer the laws of physics that govern how those atoms attract and repel each other. And then you just hit go and watch the protein fold. The problem is that the calculations are monstrously complex. Even for a small protein, and even with the world's most powerful supercomputers, simulating a few microseconds of folding could take months of computer time. It was just too slow. Projects like Folding Home were created to tackle this, distributing the calculations across thousands of personal computers of volunteers around the world. These efforts provided invaluable insights, simulating the folding of small proteins and confirming many aspects of the energy landscape theory. Then, everything changed. A team at Google's DeepMind developed an artificial intelligence system called AlphaFold. AlphaFold was trained on the known structures of tens of thousands of proteins. It learned the complex rules that connect an amino acid sequence to its final 3D shape. In 2020, AlphaFold was able to predict the final folded structure of a protein from its amino acid sequence alone with staggering accuracy. It solved a problem that biologists had been working on for 50 years. Now, it's important to be clear about what AlphaFold does and doesn't do. It predicts the destination. It gives us an incredibly accurate picture of the final folded structure, the bottom of the energy funnel. It doesn't, however, simulate the journey. It doesn't show us the protein actually folding in real time. It doesn't explicitly calculate the physics of the hydrophobic collapse or the formation of hydrogen bonds. It uses deep learning to recognize patterns in the sequence that correspond to patterns in the final structure. But by giving us the final structure, AlphaFold provides a crucial piece of the puzzle. Knowing the destination makes it much easier to figure out the likely path. Scientists can now use AlphaFold's predictions as a starting point to run more focused simulations to understand why a particular protein folds the way it does and what might happen if its sequence is mutated. So we have come a long way from Levinthal's paradox. We know now that proteins don't search randomly. They are guided by a symphony of physical forces. The process is dominated by the powerful hydrophobic effect, which rapidly collapses the chain and then fine-tuned by a network of weaker interactions. The entire journey is a downhill slide on a pre-programmed energy landscape, a funnel that was shaped by billions of years of evolution to be fast and efficient. It's a process of organized collapse, not random search. The instructions are not in a blueprint, but in the very nature of the beads on the string and their love or hatred of the water around them. It's a beautiful solution to an impossibly complex problem, and it's happening inside you right now, countless times every second, building the tiny machines that make you, you. It's the frantic, microscopic, and perfectly choreographed dance that underpins all of life.